Hi class, this section is on complex numbers. So complex numbers arise when you're taking the square root of a negative number. So that's how the number system was invented, because someone had to come up with a definition for when you're taking the square root of a negative number. So we call that the imaginary unit, and it's I equal to the square root of -1. And if you square both sides, on the left side, you'll get the I squared, and on the right side, you get this radical to cancel out, and that's how you're left with -1. So this is an identity that we're going to use. So this is important to know, as well as this. So for the first example, they want us to write the expression with I notation. So what you can do is you can treat that square root of 49 as square root of 49 times the square root of -1, which is 7i. Because this is 7, and the square root of -1 is I. So that is your answer. Let's look at the next one. This 7 is not a perfect square, so you can do the same thing that I just did. Radical 7 times radical -1, which is just radical 7i. However, you don't want to put the I in the back because it might look like it's inside the radical, which it shouldn't be. So we write it in the front in that situation. The next one, you have a negative on the outside, and then you can break that up into 4 times 5 times -1. So I broke up -20 into 4 times 5 times -1. I chose 4 and 5 instead of 10 and 2 because 4 is a perfect square. So that becomes negative, and then that becomes 2. That stays radical 5, and that becomes I. But remember, the I, we want to put it in front of the radical. That takes care of that problem. So a complex number is a number that can be written in this form. So a plus bi, where a and b are real numbers. This is called the real part, and this is called the imaginary part. So let's add these two complex numbers together. It's just basically combining like terms. So if you add 3 and -8 together, you should get -5. And if you add -5i and +i, that'll give us -4i. For the next example, same thing. We do have to distribute that negative. So this becomes 7i minus 1 minus 3i. And then after combining like terms, you do want to put the real part first, so that would be -1, and then the imaginary part second, which would be +4i. Here we are multiplying two complex numbers, and you can do the same thing, which is FOIL. If you like the FOIL method, that's 10. That's -2i, +15i, -3i squared. And I squared, we know, is really -1. So I'm going to just replace that I squared with the -1. And then I'm going to combine these like terms. So if we do that, you should get 10 plus 13i. And here you have a -3 times a -1, which is a +3. And now we can combine like terms. 13 plus 13i is our final answer. Same thing here. I'm going to show you guys a different method to multiply. It's called the box method. Okay, so let me draw a different, nicer box. All right, and this is a 2 by 2, so I'm going to put 2 rows and 2 columns. So you can put 6 and 7i here, and you can do 6 and -7i there. And then you just multiply the row and the column to get the number that goes inside each box. So this would be 36. 42i, -42i, -49i squared. And remember, I squared is -1. So this is really +49. And now we can combine like terms. So like terms, these are like terms, and they actually are opposites. So they cancel, and these are like terms. So we have a 36 plus a 49, which is going to be 85. So whenever you're multiplying two conjugates, complex conjugates, the imaginary part will always cancel out. That's the nice thing about multiplying two complex conjugate factors. The i's will always cancel out, and you'll always be left with just a real number. And that's what they say down here. Complex conjugates, if you're multiplying two complex conjugates, your final answer will not include an I. So that's what we're going to do here. This is similar to rationalizing a denominator because I is really radical negative 1, and it's in the denominator, so we're sort of rationalizing. And the way we do that is similar to before. We're going to multiply by the complex conjugate, which is 9 minus 3i, top and bottom. The top is just going to be 9 minus 3i. The bottom, we can do that box method again. So here's my box, 2 by 2. And here we're going to have 9 minus 3i, 9 plus 3i. This is 81, 27i, negative 27i, negative 9i squared. The I squared becomes a negative 1. And now we can combine like terms, which cancel out, and like terms. So those like terms are 81 plus 9, which is 90. All right, and because we want to write this in as a complex number, that means we have to separate this into two separate fractions. So the first fraction will be 9 over 90 minus 3 over 90i. And we can simplify these two. That becomes 1/10. This becomes 1 over 30i. The final problem is the same type of problem. We have to rationalize the denominator, so I'm going to multiply by the conjugate once again, which in this case is 2 plus I. Right, so if you FOIL, you can do the box method if you like, or you can just do the FOIL method, whatever you're comfortable with. I'm going to go ahead and do the FOIL method first, outer, inner, last, and I'm going to get 8 plus 4i minus 2i minus I squared. The denominator, same thing. I'm going to get 4 plus 2i minus 2i minus I squared. And then I'm going to change those I squares to be negative 1s. So the numerator becomes 8 plus 2i after you combine like terms. And then the double negative here, minus minus, becomes a plus 1. And similarly on the bottom, these will cancel out, and you will also have a double negative, which becomes plus 1. And now in the numerator, we have 9 plus 2i. In the denominator, we have 5. And then the final step is to separate this into two separate fractions. So our final answer should be 9/5 plus 2/5 I. And that concludes, oh no, there is one more page. Sorry about that. And here it is. So we're looking for powers of I. So whenever you have powers of I that are greater than 2, the easiest way, I think, is to just try to write this in terms of I squared, because we know I squared is equal to negative 1. So what I mean by that is you can write this as I to the 9th is the same thing as I squared to some power. Well, you may not get to 9, but you can get as close as possible without going over. And that would be 4, because 4 times 2 is 8. If you go 5, then you've gone over. So you don't want to go over. That would be 10. So we have to go with 4. So 4 times 2 is 8, and that means you still need one more I, so you have to multiply by an additional I to get that one that you're missing. So now you have 8 plus 1 is 9. The reason why I wrote it this way, because I know I squared is equal to negative 1 now. So this becomes negative 1 to the 4th times I, and negative 1 to the 4th power, because 4 is even, that becomes positive 1 times I, which is just I. And that's how you can go about doing higher powers of I. Let's try another one. So similarly, our goal is to make this in terms of I squared. And remember, we want to get as close as possible to 37 without going over. So that would be 18 because 2 times 18 is 36. But that's 36, which means we need one more I to complete the 37, so times an additional I. So now we have negative 1 to the 18th times I. Once again, just as the previous example, 18 is an even number, so this becomes positive 1 times I, which is I. The final problem is the same thing. The only difference is now there's a negative exponent, which means we need to take the reciprocal of that. So the reciprocal is 1 over I to the positive 56. And then we do the same thing that we've been doing, writing that I in terms of I squared. So in this case, we need to get to 56. And I believe it's going to be 23. 23 times 2 is, that's 46, so it's going to be 28. 28 times 2 is 56. And so this time we don't have to multiply by an additional I, because 2 times 28 is 56, so you don't have to multiply by I like we did in the previous two examples. And so this becomes 1 over negative 1 to the 28th power, and that's an even number, which makes that 1. And that is our